Okay, morning everyone, and thank you for the organizers for this really amazing talk. And it's a pleasure for me to be after Christian and after Federico for their amazing work on finite element methods and Costa-Road models, which have inspired me a lot for my work. So my presentation will be about presenting a framework for modeling and simulation of soft robots with which can be, let's say, which can derive, let's say, accurate and computationally efficient model for their implementation. And the pillars on which the work is based on is differential geometry and skew theory, and from the other end, Costa-Road theory and the finite element method. So this framework can accommodate the modeling of what are defined as continuum soft robots, as articulated soft robots, or also hybrid soft robots, namely articulated soft robots with continuum parts which are articulated in a serial and parallel kinematic chains. Here you can see an example of structure which is composed by a closed chain, a serial chain articulated in a rigid and soft bodies. So let's start with the continuum part. As all of us and all of you already know, the octopus tentacle has been the main source of inspiration for soft robotics in general. And to mathematically describe these tentacles, we are looking for continuum mechanics theories. And in continuum mechanics, we can deal with monodimensional, bidimensional, and three-dimensional solids. And since a soft robotic arm has one dimension which is dominant over the two others, and we are interested in modeling, let's say, slender and robots with one dimension which is dominant over the two others, we are interested in beam theories. And among the beam theories, we are interested in nonlinear beam theories, which deals with large motions and with no approximation on kinematic variables. And one theory that is really appealing for dealing with this kind of models is Costa-Road theory. And the basic assumption of this theory is that a soft robotic arm can be seen as, let's say, the continuous assembly of bidimensional cross sections which moves on a three-dimensional curve. And according to what? According to the infinite rigid body transformations, which are defined by the internal laws of deformation. And here we see, for instance, a cross-section which moves on this three-dimensional curve. And the position of the cross-section is represented by the vector position u, and the orientation by the local triad, which define a local rotation matrix. So with respect to the continuum formulation, the position field maps, let's say, the material abscissa alpha in the homogeneous transformation matrix, which evolves in a continuous way along the curve. And this homogeneous transformation matrix is part of the special Euclidean group, the Lie group of the homogeneous transformation matrices. And this is well known that is formed by a position vector, which is the position vector which defines the position of the cross-section, and the rotation matrix, whose columns are represented by the unit tangent vector, the unit normal, and the unit binormal vectors. So let's consider the evolution along the curve, and if we take the Lie derivative with respect to the space of this homogeneous transformation matrix, a special quantity arises, and this special quantity is the invariant vector field, and the invariant vector field, which is called in screw theory the twist, or the Lie algebra in the, let's say, in the Lie group and the differential geometry community. And this deformation twist is a 6x6 matrix, which is composed on the upper left sides by the skew symmetric matrix, in this case of angular deformation, and on the upper right side by the vector of linear deformations. And so we have the special, the SA3, which is the Lie algebra associated to the Lie group SA3, which is this quantity that arises when the derivative of the Lie group is made with respect, in this case, to the space. And this quantity is really important because it's an intrinsic quantity, which is invariant under superimposed homogeneous transformation or rigid body transformations. And there is a property, let's say, a mapping, an isomorphic mapping between the 6x6 deformation twist and the 6-dimensional vectors of deformation. And in this case, the deformation vector of deformation is composed by all the components of the deformations, the axial deformation, the two shears, bendings, and the torsion. By taking the time derivative, we obtain the velocity field, so with again the velocity twist with its main components, linear and angular velocities. And the compatibility equations are, let's say, describe the relationship between the cross derivatives. In this case, the space derivative of the velocity and the time derivative of the deformation. And we define also strain energy and kinetic energy in a classic way, with one arises the well-known stiffness matrix, and the other one the mass matrix, whose components are computed in the local axis. By applying Hamilton's principles, in this case, we derive the dynamic equilibrium equations, which are PDE, and we need to find a way to discretize this PDE. So our approach is to use the finite element method, which uses helical shape functions. And why the helical shape functions? Because if we go back to the shape of tentacles, or the shape of classical robotic systems that have been developed recently, we can see that all of them are have a common primitive, a common shape primitive, and this common shape primitive is an helix. So the helix approximation could be, let's say, a suitable approximation for this for discretization of the PDE. So by looking at the kinematics, differential kinematics, since the helix is a quantity with a constant deformation, this equation is integrable, and the solution to this equation is can be done by the exponential, is represented by the exponential mapping. And the exponential mapping, in this case on SA3, is used for describing the kinematic, forward kinematics in this case. And it's basically a mapping between the tangent space where the Lie algebra is, namely the deformation, and the manifold where the homogeneous transformation matrix evolves. And this exponential mapping as this structure on SA3 as this structure on the upper left side, where the exponential map on SO3, which is the well-known Rodriguez formula, and on the upper right side, we have the tangent operator applied on the angular part of the deformation times the linear part of the deformation. And this is just an example, a kinematic example. So if we have a soft arm where, for instance, we can measure the deformations and the linear and angular deformations, in this case, just bending about zeta with and torsion about x, we can just apply the kinematics equation and we obtain the configuration along the curve. And here just to have some plot by varying the torsion and bending curvature along the arm. So by starting from again the differential kinematics in time and the compatibility equation, we can obtain the differential kinematics and statics with the computation of the Jacobian and by applying the material constitutive law. And again, by using the Hamilton's principle, we can obtain the dynamic model of the continuum soft continuum part, which is let's say a well-known expression in the community. And here, just a simple example, static one, where we have let's say a simple soft arm which is subjected to an end torque. And so by applying first the statics and after the kinematics, we get that. Get the let's say the position field, and we as already we know, the position field in this case is represented by an arc with constant curvature. And here, just another example, the Princeton experiment, which is an experiment used for when soft bodies are, in this case, slender soft bodies are subjected to end force with different line of action and different force intensities. And so our simulation results pretty well match the experimental ones at different force intensity and different line of action of the force. Here, just the plot of the errors. And now let's go to the articulated soft robots. And in our point of view, we have to introduce the definition of the joint. And let's consider a rigid arm and a soft arm with let's say H, which is let's say the motion frame. And the relative motion between these two frames can be described in the geometric screw theory framework by this matrix HJ1, which is the relative transformation frame and belongs to a Lie subgroup of SA3. So this, let's say, relative transformation frame for the articulated part would play the same role that the homogeneous transformation matrix play for description of rigid and soft bodies. And the modeling of a flexible joint can be done by introducing a spring and a damper concentrated between the two, let's say, the two bodies, and by introducing the respectively energies on the final equation of motion. And within this framework, we can accommodate the modeling of all the low pair joints, the revolute, prismatic, skew, cylindrical, planar, and spherical, by changing just a matrix which came from the Lie derivatives of the relative transformation frame. And in this case, we couple the rigid and soft links through joints according to algebraic constraints. So we, in this case, deal with differential algebraic equations. And for each joint, we have an algebraic constraint to which Lagrange multipliers are introduced in the final dynamic model. And here, so again, the picture of and the simulation of these kind of systems, which is formed by rigid and soft bodies. Here, in the first part, articulated in a closed chain, after in a serial chain with rigid and soft bodies connected together. Here, just validation examples also on a spatial flexible manipulator, which has been developed at Georgia Tech. This is a simple two-link structure, flexible link structure with three joints. And we have replicated the experiments that people at Georgia Tech have developed. And for instance, in this case, we have the comparison of the positions of the tip according to a first move, to a second move, and after to also a third movement of the actuated joints. And we have packaged the models in a solver, and the solver takes as input the geometrical topological description of the system and the behavior, which can be either rigid or soft. The joints, the typology of joints, and the actuation sources, the planar, the boundaries, the forces, and the solving parameters. As output, we have classical kinematic outputs, positions, velocities, and accelerations of nodes and joints, forces and torques at boundaries at joints location, and stresses and strains within the elements. And here, just to illustrate some simulations, I don't know if they work. Okay, more or less. On the upper left side, we have a flexible manipulator, hyper redundant and really huge flexible manipulators. Flexible manipulator with a flexible transporting a flexible payload at the end effector. And on the upper, on the bottom left side, we have a tricept in a serial parallel mechanism. And these huge, let's say, huge systems are used for the inspection and maintenance domain. And on the right-hand side, we have just simple simulation of a robotic catheter or a soft actuator used for instance, developing hand gloves for rehabilitation. And so just for conclusion, I have presented in our approach for geometric formalisms to derive the models of hybrid soft robots. We involve the finite element methods using helical shape function for space discretization. And this framework can be used for modeling simulations of what we have called, let's say, hybrid soft robots. And we have packaged these, let's say, models in a finite element solver. So I thank you for your attention.
Thank you very much, Stanislao. Very interesting presentation. Are there any questions from the audience? See, Alessandro has a question. Go ahead.
Yes, very nice presentation. I have just a question on the comparison with Georgia Tech flexible arm. So in your plot, you're comparing the result of this CDC 2017 paper under some command, I guess, with your model, the result from your model. Yes. So what was the motion involved? What was the command involved? And what type of modeling did they use in comparison with yours?
They have assumed modes model, kind of assumed mode model for their manipulator, and the command are I'm not sure if they are trapezoidal or sinusoidal motion, because it's a lot of times.
But they are.
But I can let you know for sure.
They are open loop commands, probably.
Yeah, for sure.
Okay. So you can include your open loop commands in your modeling, as well as feedback commands, or not yet?
Not yet feedback commands.
Okay. Okay. Thanks.
We still have some time. I don't know if there's any other questions from the speakers or maybe the audience.
I may ask a question, maybe. So thanks, Stani, for the great talk. I'm curious about your choice of selecting the helix as the base shape. So first of all, just to be on the same page, I guess that with helix you mean something that has a constant torsion, but does it also have like a constant curvature? Or not? So is my first question. The second is if you can elaborate more on why you selected this shape compared to others.
Yes, the shape. It's let's say the base function is a constant curvature, constant torsion, and we can also accommodate constant other kind of deformation. Let's say. And so this is the main point. And the second point is the choice of this helix, because I mean came probably from most probably from the fact that let's say complex movements can be approximated by helix shapes. And this was the main point we started on using this kind of shape function for interpolation.
Okay, thank you. So if I may ask also other questions, if you have time. And regarding the flexible link case, so right, which is the advantage of considering a discretization of rho theory compared to some like other solutions that consider small deformations?
I mean, for instance, we used we started using the Kosarat theory because in our first examples, the flexible link manipulators which undergone which are undergone really high flexible, a really high deformation due to the high payloads they transport. And so, for instance, in this case, we can see that, for instance, a more classical approach or this approach get more or less the same results. We don't have yet a comparison of the results between the large one that I presented on the last slide, but it's much more motivated from the application side, because we deal with really large payloads, transportation of really large payloads.
Thank you.
Any other questions from the audience?
I see one question in the chat.
Let me check. So there's one question, and it's about the stability of these systems. How do you prove the stability of these systems?
Yes, the stability is not proven at the moment.
Okay. I don't see any other questions, and I have a few questions myself. So my first question is about actually a follow-up question from what Alessandro mentioned, is this closed loop feedback term. So what is preventing you from doing closed loop control with these type of models?
I mean, I really would like to kind of using I mean the invertible model for doing, for instance, model-based control, but it's really hard to achieve, and there is a lot of work, and probably, I mean, yeah, Christian did some work at this with this respect, and yes, I have to study again I mean, the problem is really to have an invertible model which can, let's say, run in more or less real time to use for model-based control.
But if I can follow up, so one thing is to design a controller based on your framework, which, I mean, it's of course looks quite hard to do, but I think the question could be even, let's say, much simpler. So can you simulate the presence of a controller? I mean, someone gives you a controller, and
okay.
can you?
Yes, I never tried, but yes, I don't see the problem, because I mean, we can try to feedback the let's say the position or the nodes or the deformations, so we can try to test. I mean.
Okay, thank you very much. I have just one small more question. So you said that it's also quite, how do you say that, difficult to implement, to indeed use inverse dynamics. So I'm wondering how long do these simulations take to produce? So essentially the forward dynamics.
These kind of simulations, we can accommodate more or less 2 seconds of real simulation, 1 second of real simulation with 2 seconds of computer simulations with the step side of 0.01. This is more or less to give you an order of magnitude.
Okay, thank you.